In this part of the chapter, we're going to continue talking about molecular views of reactions in aqueous solutions. We're also going to start talking about how we measure concentrations and different ways that we calculate those. So that will be this part of the lecture set. And I just want to kind of go back again, just to kind of review some of that stuff from the last part of the first part of the chapter, where we're talking about these double replacement or metathesis reactions. And that's really what we were looking at when we were kind of doing the do-si-do between the cations, those are the positively charged, and the anion part, and where we basically swap these around to create new different compounds or new different salts. And the solubility of these salts will dictate if this forms a solid or a aqueous solution or dissolved in our solution. So the solubility is something that's going to determine if that falls out of solution. And just so you know, there are charts and things that scientists can use or chemists can use to determine if something is going to precipitate out. And this is one of those kind of charts, and there are more, this is just one version, and there are more extensive charts than this, but this just gives you a good set of different cations shown here. Everywhere from, there's some polyatomic cations, different transition metals here. And you can also see here on the top row is going to be the anions. So those are going to be the negatively charged ions with even a few different types of polyatomics shown throughout this state here. What we do is we actually will take, so for example, potassium chloride is going to be soluble generally, and that's going to be true for most potassium compounds until we get to the sulfide. So there are a few things where we see insoluble for I, and we might see something that's slightly soluble, and then there are some examples where maybe this hasn't been tested or it's not possible to get these together in solution for whatever reason. So these are just kind of a general idea, just so you're aware. And these are the concepts that we use actually in water softeners, which I'll show you in just a moment. What I want you to kind of do is think about these. You can write these down, take a screenshot, figure out if these are going to be soluble or not based off of this solubility chart. So look these compounds up, and then we have the different types of compounds here, calcium acetate, iron carbonate, and sulfur chloride. So post that in Blackboard space, use these two slides for information, and then just tell me if they're solid or soluble, or solid or soluble, or aqueous and soluble, however you want to write that out. I mentioned earlier that water softeners use this idea of the double replacement or metathesis reactions to get rid of the hardness in our water. And what's really happening is we have this sodium carbonate. This is the salt that you buy in the store, and you put that into your water softener, and they're going to remove calcium, magnesium, and iron ions, those are present in all groundwater, and they make your water kind of hard and not very soft. For example, when you're washing clothes, they don't allow for like the suds and things to kind of get your clothes as clean. So let's look at the type of reaction that's happening with the sodium carbonate and some of these ions. So if we take the sodium Na, we know sodium is going to fall apart here into that compound. It's a positive charge, and the CO3 is going to have a -2 charge. And I know that through looking at the double replacement. You could also look back at that solubility chart and know that that's a polyatomic that's going to be falling apart. So if sodium and the carbonate ion, and then we actually have two of these sodium ions and one carbonate ion with a -2 charge. And then we're going to either react these with the calcium, which is a hard ion, iron, or magnesium. And these are positively charged, so they are going to interact with the negative charge of that carbonate. And then we're going to either get calcium carbonate, iron carbonate, or magnesium carbonate. Let's look at our solubility chart. Here is our carbonate anion, and you can see that if we just go down the row, a lot of these different ions, when we're interacting them with a positively charged ion, they're going to be insoluble. Sodium is soluble, so that is the thing that we're going to mix in. That's what the salt is made of, sodium carbonate. But we can see that magnesium, calcium, iron, zinc, all of these different things that we were talking about before are going to be lead even insoluble. This is going to help to precipitate out those heavy ions out of our water and make them more soft. So the reason this actually works is because these are solids, while this compound, these are in the aqueous state because they don't react with each other to form insoluble salts. So that's kind of how water softeners work. For this next part, I'd like to discuss now how we look at how much stuff is in our liquid. So if we're looking at the solute versus the solvent concentration, and we're going to be looking at how we quantify dilution or concentration of a certain substance in our solutions. And there are different ways that we can do this. We can do a mass of the solvent to the mass of the solute. We can look at volume to volume ratios of solvent to solute, mass to volume ratios. So you just have to look at hopefully someone has told you, if they, a lot of times if you get a commercial compound that you would purchase from a company, they would or should have this listed if it's a mass to mass, volume to volume, mass to volume ratio. There's also, for very dilute things, we have parts per million and parts per billion. And that, for an example, if we have 21 parts per billion, it means we'd have 21 grams of solute per 1 billion grams of solution. So that's how we would do something like a parts per billion. So it's really tiny amounts that typically we're using, thinking about like groundwater, some of those, when we were talking about heavy water, we're talking about some of those ions of calcium or iron in the parts per million or parts per billion range typically. What we're going to focus on mostly or mainly in this section is molarity, because this is what chemists often use to describe the concentration of different types of compounds within our liquids. So something that might be common that you want to do in a workplace or even at home would be to take something of a known amount and then you want to dilute that volume into a larger space. So you can take something of higher concentration and dilute it to a lower concentration. When you do this, the amount of moles, remember we were talking about moles a few chapters ago, that is related to the molecular mass or the atomic mass of your compound and how much of that you have. So it's giving you an idea of how many atoms or molecules are in here. Now, when we just add water, that number of moles of that compound does not change. It's just giving it more space to move in. So if we have a small volume concentrated solution, we add some solvent, it increases the volume, but it still has the same number of moles in it. So we do something like this. Let's say we have a 1 molar solution in 500 mils. So what is a mole? Let's talk about that. We have 1 molar solution is equivalent to 1 mole of a compound, X, over 1 liter. That's also 1 mole of X, whatever that happens to be, over 1,000 milliliters. So that is what a mole means. 1 mole, big M, this is a big M molarity. That's telling you that we're talking about a concentration, right? And this is a number of elements in your solution, for example. So now we're looking at, if we're diluting this, we have 1 mole of solution in 500 mils. We dilute it to 0.5 moles in 1,000 mils. And what we want to use for dilutions is this equation. You may have seen it in various different ways. C1V1 equals C2V2, where C1 is the initial concentration. This is the initial volume. This is the final concentration and the final volume. And you can see here, if we do kind of work through this problem, we are going to have something that looks like this. I'm going to show you the setup. If I have 1 mole over 1 liter, that is equivalent to my 1 molar solution. I have 500 mils. I'm going to convert that just to liters because we know molarity is moles over liters, and that helps us cancel these units out. We're going to have 0.5 moles. And if I take this over here for C2, I have 0.5 moles. That's 0.5 over 1 liter. That is what molarity means. Again, it's moles over liters. And then I have a 1,000 milliliters that I'm going to convert to liters, so these units cancel out. And I'm left with a half of a mole. So that's just kind of proving you that the number of things in the concentrated versus the diluted solution doesn't change. We're just changing the volume in it. Sometimes you'll also see something like this. You might see something like volume of dilute times the molarity of the diluted is equal to the volume of the concentration, the molarity of the concentrated. So it doesn't really matter. It's just V1. That's why I always use V1 or C1 V1 equals C2 V2. It's the same idea, right? We're looking at a concentration and a volume is equal to another concentration and another volume at the correct appropriate time. So we can determine the number of moles from a concentration of 1 is always going to be equal to the number of moles on the other side after we've done that dilution. So it's useful because you can use this for, it doesn't actually matter if it's molarity though. So it could be grams per liter. We could use any of these other types of concentrations before and after, as long as you know that volume change that's going to happen. So as long as you keep consistent between your volumes, you have to stay in the same unit. So if you're in milliliters, you have to stay in milliliters. You'll get milliliters out or liters or whatever that volume you're using. And the concentration, that will also stay in that same concentration. So if you're in percent mole to mole, or percent mass to mass, or percent volume to volume, or parts per million or billion, that is going to be what you get out of that equation. All right, let's practice the use of this new term of molarity. So we're going to have something with a concentration of 16 moles per liter of H2SO4, so it's an acid. It must be used to prepare 1 liter of 2 molar molarity H2SO4. So we're going to make a dilution from a 16 molarity solution to a 2 molarity solution, and we want to make a total volume of 1. So we're going to use C1V1 equals C2V2, and we're going to put the concentrated version here. I'm going to have 16 molarity times a unknown volume. I don't know what I'm going to mix that with yet. And then that's going to be equal to 2 molar, that's my final concentration, and my final volume, I wanted 1 liter. So now we just solve for V1, and if we rearrange that, that's going to give us the 2 molar times 1 liter divided by 16 molar, and then that we can kind of simplify 2 divided by 16, and then we'll know that we get 0.125 liters. So 0.125 liters is going to be diluted to 1 liter. So that's the amount that we're going to actually take out of our 16 molar solution. And then that's going to be, if we have a 1 liter container, that's 1 liter. We're going to add, that's the concentrated H2SO4, that's the 0.125 liters, and then we're going to fill this up with water, for example. So this top part would be all water. So that would be approximately that 875 liters of water. So that's how we would use this type of the C1V1 equals C2 V2 to make a new dilution of our compound of interest. Let's look at something else that's kind of looking at the concentration of an ion. So the salt, again, that we put in for the water softener is sodium carbonate. If we have 0.150 molar so that's moles over liters of sodium carbonate, what is the concentration of each type of ion in the solution? So that means that when we're looking at the sodium carbonate, we're actually getting out 2 ions of the sodium and 1 ion of that carbonate, because these fall apart, and then these are going to be, right, we have 2 positive charges, 1 -2 charged ion, and these are going to be neutral. And the ion here for sodium is going to be, we have 0.15 moles of the sodium carbonate over 1 liter of that. That's what molarity means, and the moles over liters. And then we're going to have, for every one of these compounds, the sodium carbonate, we get 2 moles of sodium ion out for every 1 mole of the sodium carbonate. So that means we can solve this. We can cancel out the units here of the moles of the sodium carbonate, and we're going to be left with our moles of 2 moles of sodium times the 0.15, and that's going to give us the moles of sodium ion per liter of our solution. We can also look at the concentration of the carbonate ions, and we do the same process. We're going to start with the 0.15 molarity sodium carbonate, and then we're going to now look at the units here, the coefficients for these, 1 mole per 1 mole, so it's a 1-to-1 ratio, and then that version is going to be the same as the concentration of the sodium carbonate to begin with. Let's look at ways that we can prepare different solutions, and typically, like I said, we're going to use the C1V1 equals C2V2, and you'll pull your certain concentration out. Typically, if you want to do this in a very exact and precise way, chemists will use these different types of flasks that are graduated, that have a certain specific volume that we can put that in of our concentrated compound, and then usually they'll have a mark that's at exactly like 1 liter, for example, and then you can make that dilution. So usually some type of volumetric glassware where we know exact amounts, and volumetric pipettes that allows us to very precisely and efficiently and repetitively make these dilutions. Okay, so one more question I'd like you to post this on Blackboard. So what volume of a 12.1 molar hydrochloric acid solution is needed to create 250 milliliters of a 3.2 molar HCl solution? So this is the 12.1 molar, and a lot of times you'll actually see 12.1 normal. It might be an N. It really means the same thing. It might change if you have more than one hydrogen. This is just based off of how we treat acids sometimes. So sometimes you'll see an N for normal, and it just tells you how many acidic hydrogens there are. For this one, there's only 1, so it's molarity, and molar is the same as normal. So we have 12.1 molarity of HCl. We want a 3.2 molarity solution. So calculate this and post that in the Blackboard space. I do want you to make sure that you're careful when you're looking at the C1V1 equals C2V2 equation. That's really only meant to be used when we're doing dilutions. But if we're trying to figure out how much of something we want to pull out based off of the molarity, for example, we don't want to do that. So this is an example here where I'm asking how many milliliters of a 12.1 molar hydrochloric acid solution do I need to deliver to have 1.25 moles of HCl. So we would not use C1V1 equals C2V2. We'd have to do the normal stoichiometry in order to do this, or the conversion. So I have 1.2 moles of HCl is what I want to deliver. Then I would take the concentration. I would basically use this concentration as a conversion factor. So that's moles of HCl, and then I'm going to say, well, I have, for every 1 liter of HCl, I'm going to have 12.1 moles. So we should think of this concentration as a conversion factor. And so this is going to allow me then to cancel out my moles. Then I will be able to get something like 0 0.1033 liters or 103.3 milliliters of HCl will contain the 1.2 moles of HCl. So just make sure that if we use C1V1 equals C2V2, we wouldn't get this answer out. It wouldn't give us the proper solution here. So make sure that you're using this in the right space, and then we're not trying to, if we're doing chemical reactions, that's another place you don't use this. If we are looking at stoichiometry problems, don't use this. This is only that C1V1 equals C2V2 is only for dilutions, or you'll get the wrong answers. But this is really helpful in a lot of areas where you're trying to make dilutions and change concentrations. Concentrations can be really helpful for being able to determine the number of moles in a certain volume like I just showed you. So we can use the same stoichiometry techniques as we have discussed previously. And one of the ways that we use this, and it's typically called titration reactions. So it's used as an analytical technique to determine the concentration of a solute based on what you're chemically reacting with it. We can use this for quality, for water quality, or quality control, oftentimes in the food industry, where we'll use titrations to determine various things with concentrations and how much is in our food or in our water, for example. And basically, we have to know what the chemical reaction is in order for a titration to work. So we need to know what that chemical reaction is and what the stoichiometries between our reactants are going to be. Has to be rapid and come to completion relatively quickly, so we can't wait. Generally you're not going to want to wait for this to happen for 2 weeks or something, right? And we need to know the exact quantity of at least one reactant. So usually you have a certain known amount of one of your titrants, and then you're going to use that to figure out what the unknown is of your other compound. And we'll use stoichiometry then to find the amount of the other substance. So a lot of times with an acid or a base, maybe we don't know the acid or we don't know the base. You'll have an indicator that tells us that, oh yeah, this is the end point. A lot of times you'll add something that will change the color based on the pH. And once you get your equivalence point, it's going to kind of start to turn a little pink, for example. That's when we're using phenolphthalein. But if you add too much, it'll get too dark and you passed your end point. So typically, this is a lot of times done with acid bases, but it doesn't have to be that. It just has to be a chemical reaction we know, and it's rapid. Here's just an example of how this might be used if we're looking at citric acid and we want to know how much citric acid is in our orange juice. We can neutralize this with sodium hydroxide, which is a strong base. So this is nice because if we know it's a strong base or a strong acid, those oftentimes will go to completion really quickly. So that meets our needs for a titration reaction. It's controlled. We know our acid-base chemistry, although we haven't talked about it in this class yet. That's in the next section. But we can use these ideas, and we'll say that basically if we know the exact amount, the molarity of our sodium hydroxide, which is our known compound, and then we can use that to measure the amount of how much we use in our chemical reaction, and then we'll be able to use that to determine the number of moles of the citric acid. So that's kind of the idea there that we can use for this type of chemical reaction. And a lot of times we'll use these different types of instruments called the burettes, where they'll have this stopcock that helps us to deliver precise amounts of our base, for example. So our sodium hydroxide in that last example here would be our orange juice, and we're going to be able to add a very precise volume of our base into the acid, and then when we find the end point, we know that the acid and base have reacted. Then we'll be able to figure out exactly how much volume we put in there. Titrant is the solution in the burette, so that's the known amount. So that's the thing that we know the exact concentration of. The analyte is what we're analyzing. The equivalence point is when the moles of the titrant and the moles of the analyte are stoichiometrically equal. So they've canceled each other out, essentially. And a lot of times, not always, there'll be an indicator that can be used just in order to know when we've gotten to the equivalence point. And then here we have the end point is the volume of titrant required to complete the reaction. Let's look at an example of something like this. So how many milliliters of this 0.0475 molarity H3PO4 could be completely neutralized by 45 mils of 0.1 molar potassium hydroxide? The balance equation for the reaction is below. Potassium hydroxide is a strong acid. It's going to go to completion, and this is a strong base, and it's going to go to completion. This, we're going to do the same thing as our double replacement. So we take this HO3 and we take the OH and we're going to form water. And then the potassium is going to swap places with the hydrogen. So we have a K3PO4. So it's the same thing as a double replacement reaction that we've been looking at previously, but it's really an acid-base reaction. Well, we have this polyatomic and we have that polyatomic, and we are just switching partners. Sometimes I like to make water as HOH. That's the same as H2O, really. And the strategy here is to determine the moles of the potassium hydroxide. We do know that because we are given a certain amount. We have 45 milliliters of 0.1 molar potassium hydroxide. And we're going to use the stoichiometry of the chemical reaction to then determine the acid. So then we'll use that concentration to determine the number. So how many milliliters could be used to completely neutralize that. So here we have the question. We know that we have 45 milliliters of potassium hydroxide. That was given in the question here, 45 milliliters. And then we have our different, we're basically just doing a conversion factor to convert the milliliters here to liters. So that unit is going to cancel out. And then we know that we're given a compound, a solution that has a concentration. The potassium hydroxide is a 0.1 molar solution. So that was given 0.1 molar solution of potassium hydroxide. So that we can cancel those out, and then we're able to get the number of moles of the potassium hydroxide out. So that's the number of moles. We're going to use the coefficients to calculate the moles of the H3PO4 required, and it's a 1:3 ratio. If we go back to that chemical reaction, it's a 1:3 ratio here, the stoichiometry, and we're going to use those then to solve this problem. Here we have the 1:3 ratio. We're going to cancel out the moles of the potassium hydroxide, and we're going to solve for the moles of the hydrogen phosphate. So here we have the H3PO4 at 1.5 times 10 to the negative 3 moles. And now we can use that to calculate the volume of H3PO4 that we need. We take that answer, and then we do another conversion here with the 0.0475 moles that we need of the H3PO4 over the 1 liter of H3PO4. That number came from this 0.0475 molarity solution of the H3PO4. This has been described. We use that as a conversion factor to cancel out our moles of the H3PO4, and then we cancel out our liters by doing a conversion from liters back to milliliters, and then that should give us the answer of 31.6 milliliters of H3PO4. So just a way that we can kind of use this in order to solve problems in chemistry. Now, this is, again, a lot more complicated than the C1V1 equals C2V2. And this isn't going to work, again, for these types of chemical reactions. So I just wanted to show you an example of a more complex chemical reaction where you cannot use this. If we have to use stoichiometry, if we're doing chemical reactions, then that C1V1 equals C2V2 doesn't work. If you want to try one of these titration questions, here's one of the examples you can try here, looking at the 25 ml sample of the HNO3. It's titrated with calcium hydroxide. What's the concentration of the hydrogen nitrate in the initial sample? So we're going to, again, do the same thing, really just follow those steps from that last part of the video, and you're going to, I just want to make sure that you recognize that that is going to be a polyatomic. We also have HOH. Remember that water can be kind of written as a polyatomic, and we have the polyatomic here. So do your metathesis, you're swapping things around, and you'll be able to kind of, this is actually already a balanced equation for you, so you're not going to have to worry about doing anything else with this. You can just use that in order to know what the stoichiometries are for the reactants and products, and then you can use that to set up this titration. And one of these is the correct answer, so if you want to try this and post your answer in Blackboard, go ahead. It just gives you a little bit more practice with in keeping up with our our stoichiometry questions and problems, and understanding that. We'll kind of, the next section, we're going to kind of get into oxygen-based compounds, and then after that we'll get really more into the acid-base chemistry. But since I showed you those metathesis reactions, there's a lot of similarities between that and acid-base reactions, so I thought I'd introduce it during this part of our discussion on solutions.